Number one says when the rover Sojourner was deployed to the surface of Mars in July of 1997, radio signals took about 12 minutes to travel from the Earth to the rover. How far from Mars was Earth at that time? So the nice thing for us is light travels at a nice constant speed. And so that means that we can use the equation velocity equals distance divided by time. And in the case of light, we generally say c is that speed of light. Remember, Einstein called it a constant, is distance divided by time. So now for the distance, that says that it's the speed of light times the time. And so for the speed of light, we are going to use 3 times 10 to the 8th meters per second. And the time is going to be 12 minutes. 12 minutes times 60 seconds per minute is the same as 720 seconds. So I'll put 720 seconds in there. Now 3 times 700 is 2100, and 3 times 20 is 60. So that's 2160 times 10 to the 8th meters. And only 2 of those digits are going to be significant. So you might round it to 22 times 10 to the 2200 times 10 to the 8th meters, or you might make it 2.2 times 10 to the 11th meters. Take a look at the example. It says you have a Fizeau experiment, and now remember what Fizeau did. He shined a light through a cogged wheel, and the light was able to pass through one of the spots, open spots in between the teeth of the wheel. It made a long trip to a mirror, came back, and if the wheel was rotating just right, it rotated around so that the next gap was set up so that the light could pass right through it. So here they say that the mirror is 5.9 miles away, 9,500 meters away. And the time for the wheel to rotate from one notch to the next, 6.3 times 10 to the minus 5 seconds. And it says, what's the speed of light from this measurement? Well, speed of light is distance divided by time. And so I'm going to take 9,500. I'm going to take it times 2 because the light's going to go over and it's going to come back in that amount of time. So that's going to be 19,000 meters. And I'm going to divide that by the time that they said, 6.3 times 10 to the minus 5 seconds. That's a tough one to do in my head, but I did that before I started this. And I got 3.015 times 10 to the 8th meters. And the authors did a nice job on this. If you can remember, Fizeau got a number that was just a little bit too high, and they're giving us a number that's just a little bit too high here too. Now, along those same lines, it says, if the distance from the notched wheel to the mirror is increased, should the rotational speed of the wheel be increased or decreased? Well, it's going to have to be increased too, because we want the, it's going to take longer. If it used to go to there and come back, now it's going to go to here and come back. Well, it's going to take more time because it's more distance. And so that means we need to let it have more time. And so we're going to slow the wheel down some. So we're going to decrease the rotational speed of the wheel. Remember, rotational speed of the wheel was omega radians per second. And so that's it. How long does it take for the light to return to the notched wheel if the distance to the mirror is 10.5 kilometers? Well, I'll take that speed of light as distance divided by time, and I'll say that the time is the distance divided by the speed of light. I wasn't sure if I should use the little bit too big speed from before or the one that I know. Hey, they ask how long does it take the light to return, so I'm going to use what I know is the modern version of the speed of light. And so 10.5 kilometers times 2 is going to be 21 kilometers. And or times 10 to the 3rd meters, and we're going to divide by 3 times 10 to the 8th, 3.0 times 10 to the 8th meters per second. You can see this is actually fairly easy to do. 21 divided by 3 is 7, and I'm going to take that 10 to the 8th to the numerator. Think of it as times 10 to the negative 8, and so that's times 10 to the negative 5 seconds. Pretty fast. On number 12, it says light year is a unit of distance. It's the distance that light travels in 1 year. How many kilometers are in the light year? So this is really just a application of saying that the distance is equal to the speed times the time. And I'll say that the speed is 3 times 10 to the 8th meters per second times the time of a year. Now, I want the time units to cancel out. So yeah, I know that it's 1 year, but I'm going to say that it's 365 and a quarter days, and I need to convert to seconds. Now, if you do 24 times 60 times 60, you'll get 86,400 seconds each day. And if you go ahead and multiply that through, you're going to get 9.46728 times 10 to the 15 meters. Now, they wanted kilometers. So the way I think of that is I think of, all right, well, that's times 10 to the 12 times 10 to the 3rd meters. And right there are my kilometers. And so I'm going to say that this distance of a light year is 9.5 times 10 to the 12th kilometers. Invisible man in number 42, he wouldn't be able to see anything. Why not? Well, if you're invisible, that means the light is just going to pass right through you. So here's our invisible man. Okay. And the light just passes right through him, right through his eyeballs and everything. So he has to pass right through, because the person over here that isn't invisible needs to be able to see, you know, whatever was over here. If any of that light is sucked up by his eyeballs, absorbed by his eyeballs, and turned into a signal for his brain, then this person would notice it and they wouldn't be invisible anymore. So the invisible man is going to be invisible because light's going to pass right through him, and that means his eyes aren't going to be able to absorb any light, and so he's not going to be able to see. Number 53 is a neat one. This is the Galileo experiment for determining the speed of light. And we know that the Galileo and the assistant weren't able to get far enough to make this thing a success, but it's kind of neat to see how it would have worked. And so it talks about Galileo attempting to measure the speed of light with these lanterns. If you can remember, Galileo would have opened up a shade on the lantern and sent a flash of light over to an assistant that was pretty far away. And then as soon as that assistant saw the light, they were going to flash the light back, and Galileo would be able to then measure the time that it took from the first time he sent a pulse till it came back, and that would be the time, and then the distance divided by time would be the speed. It was a good idea, except that this time was just so fast. Well, here they say that human reaction time is about 0.2 seconds, and they want to know how far away would you have to be so that the human reaction time wouldn't give you worse than a 15% error in the measurement. Now, the thing about this is it's not that it's going to give you too slow, it's going to give you too fast of a thing. And so all it is to say that the speed of light that we're going to observe with this, if we're no more than 15% away, it's going to be 85% of the speed of light. And so we're going to say we're looking for 85% of the speed of light, 85% of 3 times 10 to the 8th. And that's going to be the distance that it travels, 2 times the distance between the observers. That D is the answer. And divided by the total time. Now, the time is going to be the time that it takes to actually do the traveling plus the reaction time, because the reaction time is going to add on a little bit of extra time there. And so in the denominator here, I'm going to add a t, that's the time of the light actually traveling, plus, and we're hoping this spot is not very appreciable, but that delta t is the reaction time, the extra time that was added on to the measurement. Okay, so now the time, this time right here, of course I don't know it, but what I could do is I could make that the speed of light divided, or 2 times the distance divided by the speed of light. We all know that speed of light is distance divided by time, and so time is whatever the distance is. Here, 2 times the distance between the observers divided by the speed of light. And so there we go. Don't be thrown off by the 2. This d means whatever distance it's traveling in that much time, and in this much time t, it's traveling 2 of those d's right there, plus that little bit of extra time down there. Okay, And so now what I'm going to do is that's 85% of the speed of light again. And so now I'm going to cross multiply this, and I'm going to make this 0.85 c times 2d over c plus delta t, that's my 0.2, and that's equal to 2d. Okay, so now how about we distribute here, and we're going to get 2 times d times 0.85. The c's canceled out there, but not on the second part, plus 0.85 c times delta t, and that's still equal to 2d. Let me go up here. Now what? Now let me say 2 times d times 0.85 is 1.7d plus 0.85 c times 0.2. 0.2, remember, was the reaction time for the human. And that's equal to 2d. And now I'll take the 2d, I'll get this term with the d over to the other side, and it's going to be 0.3d, and that's equal to 0.85 times speed of light times 0.2. Now we know that the speed of light is 3 times 10 to the 8th, so I'll make this 0.85 times 3 times 10 to the 8th times the 0.2, and I'll divide that by the 0.3, and that'll give me the d. And if you go ahead and put this through, you wouldn't think it would come out this nicely, but it actually comes out to 2 times 10 to the 8th meters. Now, if you're thinking that's really far, you're right, that is really far. In fact, I looked it up. The circumference of the Earth is actually 40 times 10 to the 6th meters, aka 0.4 times 10 to the 8th meters. So you can see that that distance right there is like 5 times around the Earth. So how are you going to be able to get those two that far apart? I mean, the flashlight would have to go here. You have to go around, 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 and then the partner would be right there. That isn't going to make any sense. So this was a good idea by Galileo, but the Earth's just not big enough. Number 54, they talk about Michelson's experiment to measure the speed of light. Now, Michelson did a thing very, very similar to what Fizeau did, but Michelson improved it because he used an 8-sided mirror like they're showing in the picture. And the benefit there is, if you got the 8-sided mirror, you're timing how long it takes the mirror to go maybe from there to spin around, well, if it's 8-sided like this, 1/8 of a time, and you end up in this position. See what will happen? If the mirror's spinning a little bit too slow, then when this face moves up to there, it'll only be in that position, and the light will go over there like that, too slow. Versus if the mirror is spinning too fast, it'll be past that angle that they have shown there, and it'll go over here. But if it's spinning just right, the way they originally had that pictured, then it will be like that, and right into the eye. And so all that is to say, this is an advancement because you don't have to wait for a space to open up. There's more of an instantaneous time whenever the light is traveled that distance, and it's a little bit more of a precise measurement. Now, all that is to say, the time that they give us is in revolutions per second, and they say if the light is going to travel over here 71 kilometers round trip, they say how far or how much speed does the light have here? Well, easy enough to do. The speed of light is going to be the distance divided by time. Now, if they tell us that it's 528 revolutions per second, that means in 1 second there are 528 revolutions, or 528 cycles. And so that says that the time, this is a way to figure out the period, that says that the time, now this is really, really short, 0.00183939, and lots of repeating 39s seconds for that to happen. Now, that's not the time that it takes the light to make the trip. So that's the time for the mirror to go around once, but the light is going to travel around in an eighth of that time. So my plan is I will take that number, I will divide it by 8, and that'll give me the time for the light to make the trip. So now all I have to do is take my 71 kilometers, or 71 times 10 to the third meters, and divide by an eighth of that time I originally calculated. When I go ahead and do that, guess what? 299,904,000 meters per second. Round that off, 3 times 10 to the 8th meters per second. But you knew that's what it would come out to.